The question we want to be able to answer today is what would be a good estimator for sigma squared? So previously we talked that x bar is a good estimator for mu. And we showed that that the bias of x bar is equal to 0. So we showed that x bar is unbiased. Well, we're going to go through that same process to come up with an estimator for sigma squared to see if an estimator is a good estimator. So let's first start with the definition of sigma squared. This is equal to the expected value of x minus mu squared. Well, if we have all the data from the population, then we have 1 over n summation of xi minus mu squared. But what we don't have is we don't have the entire population. All we have is a sample. So we have little n. We don't have mu, but we could substitute x bar. So our proposed estimator is, we'll call it sigma squared mom, short for method of moments, is equal to 1 over little n summation of xi minus x bar quantity squared. And if this is good, then the expected value of sigma squared mom should equal sigma squared. So this is what we want to be able to show. All right, so to be able to show that, we're going to first put a few tricks in our bag to think about. Okay, so one is that x bar is equal to 1 over n summation of xi. And so this implies that the summation of xi is equal to nx bar. I just multiplied both sides by n. So this is one trick we're going to use. Another trick we're going to use is that the variance of xi is equal to sigma squared, which is equal to the expected value of xi squared minus mu squared. Well, this implies that the expected value of xi squared is equal to sigma squared plus mu squared. I just added mu squared to each side. And the third trick we're going to use is that the variance of x bar is equal to 1 over n sigma squared, which is equal to the expected value of x bar squared minus the expected value of x bar squared. Well, this is equal to the expected value of x bar squared minus, what's the expected value of x bar? Well, it's mu squared. And so this implies that the expected value of x bar squared is equal to 1 over n sigma squared plus mu squared. I just added mu squared to both sides. So these are 3 tricks that we're just going to lay out right now that as we go through this proof, we're going to use those as they happen. So now let's go back to this, is we want to show that the expected value of sigma squared method of moments is equal to sigma squared. So let's start on that. So we have the expected value of 1 over n summation xi minus x bar squared. Okay, and we want this to equal, at the end, sigma squared. And so we'll see if it does. Okay, this is our goal. So let's go here. Well, this is equal to, actually, let's just erase that line so it doesn't get in our way. So this is equal to, I'm going to pull out the 1 over n, the expected value of the summation of xi minus x bar squared. Well, I can then FOIL out that quadratic. So 1 over n, expected value of the summation of xi squared minus 2x bar xi plus x bar squared. Now that I have that, I can do a little trick. Or before we do the trick, let's go ahead and bring the summation all the way through. 1 over n, the expected value of the summation of xi squared minus the summation of 2x bar xi plus the summation of x bar squared. Well, now that I have those, this is equal to 1 over n, the expected value. Let's do one more change. The summation of xi squared minus, well, the 2 and the x bar are constants, so it's 2x bar summation of xi plus this x bar squared is also a constant, so it's n x bar squared, and we go there. Now let's focus on just this middle term here. So 2x bar summation of xi. What I can do with that term is I can multiply and divide by n over n, because that's just 1. And so now I get 2x, sorry, this should be x bar here, 2x bar n times 1 over n summation of xi. And so that is equal to, well, this is right here, x bar, whoops, not x squared, but x bar. So now I get this middle term is going to be 2n x bar squared, because I have an x bar here times an x bar here, so that's going to be an x bar squared. So with this, let's put this back into our equation right here. So this is equal to 1 over n, the expected value of the summation of xi squared minus 2nx bar squared plus nx bar squared. And now we have a minus 2nx bar, a plus 1nx bar. So this is equal to 1 over n, the expected value of the summation of xi squared minus n x bar squared. So there we have that. Now with this is, let's go look at our tricks. Notice that xi squared, or rather before we do that, let's go do one more line and then we'll use our tricks. This is equal to 1 over n summation of the expected value of xi squared minus the expected value of n x bar squared. I can pull out this n right here. So I get 1 over n summation of the expected value of xi squared minus n, the expected value of x bar squared. Now let's turn to our tricks. Notice that we have expected value of xi right here. I can plug that into there, and I have expected value of x bar squared. I can plug that into there. And so let's go ahead and do that. So this is equal to 1 over n summation. Well, what do we have for xi squared, or expected value of xi squared? We had sigma squared plus mu squared. This is 1 over n times all of this. So real quick, just go back to make these notes a little more complete. There we go. So 1 over n times that minus n. What do we have for the expected value of x bar squared? Well, we had 1 over n sigma squared plus mu squared. And that's the trick that gets rid of all of our xi's and x bars and put things in terms of population parameters. Now I just have to work my way through. So this is now 1 over n times this summation here. There are no subscripts, so these are both constants or parameters. So this is n sigma squared plus n mu squared minus, these n's cancel, sigma squared minus n mu squared. Now I see that this will cancel with this. And so I'm left with 1 over n times n sigma squared minus sigma squared, which I can rewrite as 1 over n times n minus 1 sigma squared. And so now we get the final equation, n minus 1 over n sigma squared. So this is what the variance, or rather not the variance, but the expected value of sigma squared mom equals this, which does not equal sigma squared. So we showed here that this sigma squared mom is biased. Or in other words, this estimator we have right here, where instead of the population, we use a sample of n, and instead of mu, we use x bar, that this is a biased estimator. So let's go ahead and write what we found right here. The expected value of sigma squared mom, which is the expected value of 1 over n xi minus x bar squared, does not equal sigma squared. So this means that it is biased. But the question we want to be able to ask is, well, if that's biased, is there something else we can come up with that might be unbiased? Because this right here was n minus 1 over n sigma squared. Well, what if we were to come up with something a little closer to what we had? And so what if instead we were to say, let's let s squared equal n minus 1 sigma squared mom. Well, if I did that, then the expected value of s squared would equal to n minus 1. I could pull out that, times the expected value of sigma squared mom was n minus 1 over n sigma squared. And so these would cancel, and I would be left with the expected value of sigma s squared is equal to sigma squared. So that's the unbiased estimator. So what's the actual estimator? Well, s squared is equal to n over n minus 1 sigma squared mom, which is 1 over n summation of xi minus x bar squared. Well, notice that those n's cancel, and so s squared is equal to 1 over n minus 1 summation of xi minus x bar squared. This here is an unbiased estimator for sigma squared. And we call S squared the sample variance. So that is why the equation for sample variance is 1 over n minus 1, is because that's what's needed to make S squared an unbiased estimator for sigma squared. So the question we were asked to start is, what would be a good estimator for sigma squared? Well, we used the equation for sigma squared to come up with a proposed estimator. We showed that estimator was biased down here. And then using that bias, we're able to come up with a new estimator that is unbiased. And there is our new estimator for sigma squared. The population parameter is the sample variance, which is 1 over n minus 1, the summation of xi minus x bar squared.